The first type of bond we're going to look at closely is covalent bonding. Now, if you remember, covalent bonding is when electrons are being shared between two atoms. And when we have compounds which are participating in covalent bonding, their representative particle is referred to as a molecule. So a molecule is a neutral group of atoms that are held together by covalent bonds. And we refer to this chemical compound as a molecular compound. And with molecular compounds, we have a molecular formula which tells us the types and numbers of atoms combined to make a single molecule of the molecular compound. And some examples we have here are water molecules. H2O would be its molecular formula. Oxygen molecule, if you remember, oxygen's diatomic, its formula would be O2. And all the diatomic elements have a representative particle that's a molecule. And a sugar molecule, where we've got lots of atoms, C12H22O11 being its molecular formula. Now, when these bonds are forming, bonds form because of energy. And when we think about potential energy is energy an object has because of its composition or perhaps its position. Probably the funnest or the most fun thing about potential energy is when you are riding a roller coaster. Because when you think about your roller coaster ride, you start off and the first thing they do is they take you to a big top rise. And then you're going to go down and you're going to do a bunch of other loops. So, but what's happening on this very first part of the trip is that it's taking potential energy to a maximum. And that's where we have energy due to its position. Well, position relative to the ground. So this is our maximum potential energy, and once I get to the top, all of this becomes converted to kinetic energy as the object's in motion. Now we notice a lot of times with roller coasters, our hills aren't as big later on as they are in the beginning because we're losing some of that energy due to friction. Now, when we're looking at atoms and the potential energy because of their position, that's their position in relation to each other. And this bond will form when the potential energy is at a minimum and we'll have a stable molecule. So here's what happens when we're looking at a bond forming between two hydrogen atoms. Well, first of all, we're going to notice that with two hydrogen atoms, where there's going to be places where we're going to see some repulsion, and we're going to see some places where they'll be attracted. And there's a balance somewhere. If they're too close together, as in here, okay, we're going to have a lot of repulsion because our nuclei are too close together. Here, they're almost too far apart in order not to be attracted to each other. So the closer the two atoms get to each other, okay, and this is representing internuclear distance, which means the distance between the two atoms. So as these atoms get closer together, what we see is potential energy. This line is representing potential energy. It becomes lower and lower and lower. And at some point, we will reach where we have an optimal bond length, which means the distance between these two. And at that point, we've got our potential energy at a minimum. So looking at that balance of forces between electrons repelling, nuclei repelling, and the attraction of the nucleus of one atom to the valence electron of the neighboring atom, all of these things balance out and form a bond at a length when potential energy will be at a minimum. Now, when we're looking at characteristics of covalent bonds, now when we're looking at characteristics, we're looking at what's going on with the electrons in the bond between the atoms. First, characteristics. Well, electrons are shared between atoms at the overlapping part of their orbitals. So if I look at, for example, HF and HI. Now, when they're bonded covalently, they've got a region which they overlap. Here, I can see an overlapping region, and here I can see an overlapping region. So where the valence orbitals overlap, that is where the bond forms. And you probably notice something interesting here. This overlapping region between the hydrogen and the fluorine almost looks bigger than between the hydrogen and the iodine. Likewise down here, this overlapping region between the two fluorines is bigger than this overlapping valence region of the two iodines. Why is that? Well, because iodine is so much bigger, it's harder for this nuclei to be as attracted to valence electrons in this outer part of the neighboring atom. Well, here our atom is smaller, so this nuclei is going to be able to have more of an attraction for an electron in that neighboring atom. So the bond forms because the valence orbitals are overlapping. Now, when we're looking at breaking bonds, energy is needed to break bonds. That's what we call the bond energy. So if I'm putting energy in to break a bond, that would mean that when the bonds come back and reform, energy is going to be released. So if we would take a look at this chart, okay, here we've got potential energy is green, and the blue represents any kind of heat or light energy, because a lot of times, especially when we're looking at combustion reactions, we've got a lot of heat and light energy is released. So here are my individual molecules. All right, this could be like an oxygen and 2 hydrogen molecules. So we're putting some energy in and breaking these bonds. Okay, what happens? When the bonds are broken, our potential energy actually increases, because the energy that we put in to these units becomes stored in the individual atoms as potential energy. And when these things go back together, so let's say for example this was oxygen and hydrogen atoms, they will reform water. And if you think about what a hydrogen explosion looks like, if you ever saw real footage of the Hindenburg, when those bonds reform, we do have a lot of heat and light energy given off. Hence, notice that this blue bar is so much bigger now. Heat and light energy, all the potential energy that we had from these atoms being separate are now being converted to the heat and light energy. Bond lengths. Bond lengths and bond energy vary between atoms. There's no set rule for that, but we can see patterns. All right, in your book on page 182 is a table of bonds and bond energy, and this one is also one we can use as an example. We do notice that, let's just say if we compare carbon-carbon bonds, well, this would be a bond order of 1 because it's a single bond. This one would be a bond order of 2 because it's a double bond, and bond order of 3. Now, what's the pattern that we see here between the single bond to the double bond? The bond length actually gets shorter. So a triple bond is a shorter bond than a single bond. But look at what happens with the energy. The bond energy, the energy needed to break that bond. So then when I try to break that shorter bond, I'm needing a whole lot more energy in order to break that bond. And we see the same pattern with the nitrogen, single, double, and triple. Again, single, double, and triple. And notice that nitrogen's bond energy, triple bond energy, is more than carbon's. This is some of the strongest bonds found in nature, the nitrogen bond. And then we also see differences in bond energy, whether it's atoms that are bonded aren't the same, like carbon-oxygen and single bond and a double bond. So bond length and bond energy, there's a relationship. As the bond gets shorter, the energy to break that bond becomes greater. Now, bond formation follows what we call the octet rule. Now, remember that all of these elements want to be like the noble gases, which have 8 electrons in their outermost energy level. So when bonds form, they follow this octet rule. Octet rule says that atoms will gain, lose, or share one or more of their valence electrons in order to achieve a filled outer electron shell. And the ones that we see a lot with double and triple bonds are the hydrocarbons, where we've got carbon, single bonds, double, triple bonds. And one nice thing about carbon, or an interesting thing about carbon, the fact that it can form 4 covalent bonds. So bond formation follows the octet rule, and sometimes to follow the octet rule, we see double and triple bonds that have to actually form. Now, just a refresher on valence electrons. Remember, valence electrons are in that highest occupied energy level of an element's atom. The valence electrons are actually what determines the chemical properties of the element. And when atoms become in compounds and they form ions with noble gas configurations. If you remember, we talked last chapter about how metals will lose electrons to be like a noble gas. Non-metals will gain electrons so they can be like a noble gas. All of that is related to the octet rule. Now, when we want to represent an atom with its valence electrons, we use what we call an electron dot notation. And what this does is it shows valence electrons around the element symbol represented as dots. So since sodium has 1 valence electron, notice that sodium has only 1 dot. 1 dot. Magnesium has 2 valence electrons. Notice 2 dots. Now you notice that as we go across the row and we increase the number of valence electrons, notice that we're putting 1 dot on each side. Now what happens when we get to nitrogen? Now we have pairing up going on. We've got a pair of electrons here, and we have the other 3, 1 on each side, and so on, until we would get to 8 electrons with neon. So electron dot notation is how we represent an atom with its valence electrons. And when we're looking at bonding, the valence electrons are the only ones that we're concerned with, because those are the ones that are involved in forming bonds. Those are the ones that are responsible for all of the reactions that we see. So if I wanted to write an electron dot structure for aluminum, okay, I've got aluminum symbol. I look at where is aluminum on the periodic table. It's in column 3A. I would put 3 dots. It's that simple.